Hello, everyone. My name is Amir, and I'm going to talk about the paper Carsten Witt and I have done from the Technical University of Denmark. The paper is entitled Stagnation Detection with Randomized Local Search, which is mostly about parameter control techniques on multimodal optimization problems. The broader context of this talk is runtime analysis of self-adjusting evolutionary algorithms. Self-adjusting evolution algorithms can learn good or even near optimal parameters on the fly. For example, 1 plus lambda lambda GA using one rule can adjust the mutation rate on 1 max and can optimize this function in linear time. As you can see on the slide, when the algorithm makes an improvement, it increases the parameter lambda, otherwise it decreases that parameter. Another self-adjusting algorithm, 1 plus lambda EA with 2 rate, creates half of the offspring with 1 rate and the other half with a different rate. And then it adjusted the mutation rate to the one used by the fittest offspring with some probability. Now, assume that the current stage point is a local optimum. And in this situation, large mutation rates are better to escape from the local optimum. But as you can see, the mentioned algorithm set the mutation rate to its minimum. So they usually perform poorly in local optima. So in the last GECCO 2020, we proposed a mechanism called stagnation detection, which can be added to existing algorithms and make them able to leave the local optima. But in this talk, we are going to show that using a stagnation detection with randomized local search can be even much more efficient than the original stagnation detection version. Okay, so let's get started with some basic definition. Assume that f is the fitness function we want to optimize. We call the gap of a point x the Hamming distance from the current search point to the points with strictly larger fitness function values. Actually, it's not possible to improve fitness by changing less than gap of x bits. So the algorithm has to fill at least gap of x bits to make progress. Based on the definition, on unimodal functions, it's always possible to make an improvement by changing just 1 bit, like 1 max, which equals the number of 1 bits in a string x. But on multimodal functions, there's at least one point where the gap size of point is larger than 1. And so there are no improvements in the distance of less than gap of x. Like jump functions, this function for m at least 2 is multimodal and has a local optimum with gap size of m at the set of points where the number of 1 bits is n minus m. So in order to overcome this local optimum, n bits have to fill it simultaneously. Okay, so there are two types of mutations, global mutations and local mutations. In global mutations, in one step, any point in the search space is accessible. For example, the mutation that we have in classical 1 plus 1 EA, which flips each bit with ascent S, or actually mutation rate S over N, there is a chance to see any search point in the search space in only one step. But local mutations can only create a fixed set of offspring points, like the mutation we have in RLS, which flips exactly S bits in each iteration. For example, RLS with ascent 1 can only produce N offspring. Local mutations can outperform global mutations. For example, on unimodal functions on 1 max, RLS is faster than the 1 plus 1 EA by a factor of E. And we also can say that on multimodal functions where we know the gap size, local mutations can make progress with a better chance. And according to these facts, in this paper, we study a stagnation detection with local mutations. Let's look at the original stagnation detection first. In this talk, the problem that we want to investigate is making progress with the current search point x such that the gap of x equals m. It means that m bits have to flip simultaneously to make progress. If we consider the classical 1 plus 1 EA with mutation ascent S, or in other words, the mutation rate S over N. When the ascent is 1, the improvement time of 1 plus 1 EA would be theta n to the power of n. However, if we know the gap size of the current stage point, then by setting m, the gap size, as its ascent, we can achieve the result of En over m to the power of n. This ascent is actually the best rate for 1 plus 1 EA with static mutation probability. But unfortunately, in the real world, we don't know how large the gaps are usually. Now, let's consider the following situation. Assume that the ascent is k. Actually, the mutation rate is k over n. And the algorithm doesn't make any improvement in En over k to the power of k ln steps. Then with high probability, the gap size is larger than k. We use this fact to develop the stagnation detection mechanism. Here you can see the first version that was previously proposed in GECCO 20 as a joint work with Carsten and Witt. So the algorithm starts with ascent 1 and a counter. In each iteration, the algorithm creates an offspring from X by flipping each bit in X with the current ascent, which is the mutation rate S over N, and then increases the counter by 1. Then if the new point is strictly better than the current stage point, the algorithm stores the new point and then sets the ascent to the initial ascent, and then resets the counter to count the number of failures for the new stage point. The algorithm accepts points with the same fitness value only where the ascent is 1. And finally, if the counter exceeds the threshold, the algorithm increases the ascent by 1 and resets the counter to count the number of failures for the new ascent. In summary, the ascent is 1. The algorithm tries to find an improvement. In the case of not finding an improvement after some iterations, which is the threshold value, the algorithm increases the ascent to 2 and similarly to 3, and so on until finding an improvement. The parameter R in the threshold value is to control the probability of failing to find an improvement at the right ascent. In the paper, we showed that if R is set to the cardinality of image of the fitness function, we will achieve some interesting results. Now, in this paper, we would like to use local mutations in stagnation detection. The first algorithm we propose is RLS with stagnation detection, or SDRLS. Everything is the same with the original stagnation detection, but the mutation and the threshold value. We use k-bit flip mutation in the algorithm. It means that the algorithm flips exactly S bits, and the threshold value is different because the size of the neighborhood according to the mutation is different. And if you look at the algorithm more precisely, you might guess that there can be a situation where the algorithm fails to make progress. Assume that the gap size of the current stage point equals m, and there is no improvement for ascent larger than m. So the algorithm only can make progress by flipping exactly m bits. If the algorithm failed to find an improvement, because there is a randomness in the logic of the algorithm would increase the ascent to m plus 1. So the algorithm no longer can make progress. But we will show that the probability of failure is so small. As we've seen, the algorithm can make progress with probability 1 minus 1 over R. The expected optimization would be infinity with probability 1 over R. But we can see that the optimization time is n choose n, which is for relatively a small jump size, which is very good. And using a large R, like n to the power of c, which costs only a coefficient of c in the improvement time, the algorithm makes improvement efficiently with probability 1 minus n to the power of minus c. This is not so bad, but we still would like to make sure that the algorithm always works. So On the next slide, we will see a more reliable version of the algorithm. In order to resolve the issue we've seen in the previous algorithm, we propose RLS with a stagnation detection star or STRLS star. We add a new parameter radius, which is shown by R in the algorithm. This radius parameter helps the algorithm to look at a smaller strength multiple times. Actually, when the radius is 10, the algorithm checks all strengths ranging from 1 to 10. Let's look at this figure. Assume that this is timeline and this is the strength that the algorithm used. When the radius is 3, it starts with strength 3. And when the counter exceeds the threshold, it goes for strength 2 and then strength 1. When the strength is 1 and the counter exceeds, the algorithm increases the radius by 1, which is 4, and then sets the strength to the new radius. Actually, when the radius is R, the algorithm checks all strengths ranging from 1 to R descending. This approach might seem to be harmful for the running time, but surprisingly, we achieve an efficient running time. We can see that for a relatively small jump size, the expected optimization time is n choose m. And the proof is that this is the sketch of the proof that this is the event. This is the event of failure to find the actually improvement. This is the event of not escaping from the local optima, where the radius is at least the gap size. The probability of this event is small. It's at most 1 over R. So with probability at least 1 minus 1 over R, the algorithm makes progress. If we consider different radius values larger than the gap size, where the radius equals the gap size and where the radius is at least m plus 1, considering the probability of failure and the expected steps in that radius, we can achieve the expected optimization time, the improvement time. In the paper, we also present a function where stagnation detection with RLS cannot find the global optimum in polynomial time, because measuring the number of successes doesn't hint on the location of the global mutation, global optimum. I'm not going to talk about the details, but the main idea is that neat global mute function contains two sub-functions, prefix and suffix. Increasing the prefix function needs to flip only 1 bit, while increasing the suffix function needs to flip 2 bits simultaneously. You can find a precise definition of the function in the paper. However, we probably showed that the new algorithm, STRLS, needs an exponential steps to find the optimum. However, 1 plus 1 EA needs at most n square number of fitness calls. We also proved an upper bound for the minimum spanning tree problem. We showed that STRLS star can find the minimum spanning tree on a graph in these steps where there is an expected value, which is the expected number of asterisk improvements. Let's look at the proof idea. We consider the number of steps at different radius values. So the algorithm cannot make progress at radius 1 because 2 bits, actually the algorithm has to remove one edge and add another edge to keep the graph connected. So this is the threshold value and for radius 1, and this is the expected number of asterisk improvements of the algorithm. And then the algorithm increases the radius to 2. We know that the algorithm can make progress, and using multiplicative diff, we can achieve this number of iterations to find the optimum. And there is a probability that the algorithm increases the radius to larger than 2 if we consider the probability of failure and consider also the number of steps at that radius. We can see that the expected number of iterations in this case would be a small o m square. So considering different steps in the different radius values, we can achieve the expected optimization time. We ran an experiment that compares different algorithms on jump function with gap size of 4. The fastest algorithm is the fastest algorithm to find the optimum point is RLS with stagnation detection, or SDRLS star. We discussed in this paper. The fastest algorithm with global mutation is classical 1+1 EA with constant ascent 4, which is the size of the jump. The next algorithm is 1+1 EA with a static 1+1 EA with a stagnation detection. It performed roughly the same compared to the 1+1 EA with a static mutation priority, even though it doesn't need to know the gap size. The next 3 ones are 1+1 EA with heavy tail mutation with 3 different parameter beta. And the last one is the classical 1+1 EA with a standard mutation probability, which is 1/n. And finally, on this slide, we see a summary of the performance of the algorithm. The first column is for the original stagnation detection using bitwise mutation. However, the next 2 columns are for the algorithms presented in this paper, which uses k-bit Philip mutations. In this row, we can see the threshold values for the algorithm. In the second row, we can see that the improvement time where the gap size equals n, and we can see that RLS with a stagnation detection outperform 1+1 EA with a stagnation detection. This is also interesting that the like factor in the threshold doesn't appear in the improvement time unless the gap size is not too large. Also, SDRLS star is not much worse than SDRLS, which is not reliable always. And this row is the improvement time for a gap size larger than half. For example, the local optimum we have on the trap function. And finally, in this row, we can see that the algorithm, the behavior of the algorithm on unimodal functions, we can see that the first one behaves like 1+1 EA with high priority, and the second and the third one behave like RLS with high priority on unimodal functions. Thank you for listening. If there's any question or suggestion, please let us know.
Thank you very much, Amir, for this very interesting talk. Are there any questions from the audience? Okay, let me start with one that might be stupid, I'm not sure. If you mentioned the minimum spanning tree on one of the slides, right? You only considered that for the randomized local search, right? Did you look into your previous variant with the 1+1 EA and the stagnation detection there as well?
We haven't done that on minimum spanning tree, but I believe that the optimization time of the original stagnation detection would be the same. Maybe the difference is in the coefficient in the optimization time, but asymptotically, I think they are the same. Yeah.
Okay. I was just wondering because you start with a spanning tree, right? So basically, in order to get a spanning tree in the next round, you would need to flip 2 edges, right? So you need to at least have basically flip 2 bits. Is that right?
Yeah. Actually, when we are using 1+1 EA with priority 1/e, we flip 2 bits, if I'm not mistaken. But so with priority 1/e, we flip 2 bits, and we need m square ln m steps to find the optimum if we flip 2 bits. So it would be E times M square ln n. But I'm calculating on the fly, so maybe it's not
sure.
But we can see that here the coefficient is asymptotically near 1. So the new algorithm is faster than the original stagnation detection by a factor of E.
Okay, and radius 1 basically means that you just flip 1 bit, right?
Yeah.
Or did I misunderstand that? Yeah. So yeah, I was wondering about this, that you basically need radius 2 in some sense for the minimum spanning tree. But yeah, interesting, maybe for future work. Or...
Yeah.
Okay. Are there any other questions? Okay, can I ask a question about the experiments that you had on the last slide? So is that so the I'm should the previous slide, sorry, this one.
Yeah.
So is that roughly in line with the theoretical results that you're having? Because you look at 160 bits. So is that basically what you expected? From a speed up perspective. So
yes, and yes, and actually we believe that when the for constant size of the gap, the difference between the original stagnation detection and the new one would be e to the power of a constant, that the constant would be the size of the jump. But the point is that we usually consider the in theoretical results, we consider an upper bound. So in practice, it might be a bit different, but yeah, but this is the one we actually we predicted.
So this is basically confirmed what you expected. Okay.
Yeah.
Okay, very nice.
Okay. Just any
other
one
questions?
point about the jump function. So has a path of 1 max. So this is not the improvement time from escaping actually the local optimum. This is the time to find the optimum point on jump function where the huge path is unimodal. Yeah.